Assalamu alaikum everyone. So today we will be talking about simulations, and we are in lecture number 27, and we will be talking about the simulation tool. In one of our last lecture we talked about a tool that is NS2, and we have gone through the installation steps that are involved when we want to install or use that tool onto Windows, and we have also talked about its installation on Linux. These are the bullets which we will be talking about. First of all, we will try to find out that why we are using simulation tool, because we need to establish network irrespective of wireless network or wired network. So we can have both. We can have heterogeneous network where the core is actually designed using wired technology, and onto that core, on the top of that core, we have designed or developed a wireless network, and we want to simulate that, and we want to find out some of the parameters, some of the metrics, or maybe we are interested in packet loss, jitter, delay, and such. There are a lot of parameters we can evaluate. Moreover, if we want to enhance that network, and topology is very important. So we can also test and simulate certain topologies before enhancing or extending the existing infrastructure, existing network. So we will try to establish that why we need simulation tool for network analysis, and then we will be talking about the NS2, that is Network Simulator 2, and how we can get it, because it's an open source, and then how to use it, how you can use it, because there are a lot of different languages that are involved in the development of NS2. So we will try to find out that how we can use NS2, and if you want to add your own protocol, you want to add your own node, or maybe you are interested to design and develop a new router, so how you will be able to add your own stuff. So as mentioned, it is an open source tool. So normally, or this is a convention, you can say, for an open source tool, it's very difficult to find out the documentation. So we will be talking about the documentation and how we should go through certain documentations and tutorials in order to grab this tool quickly and effectively. Then as coding is involved, so there are different languages, scripting languages, there are some core languages, and there are some languages that are actually used for sequencing and scheduling. So all those languages, they can have certain bugs whenever one programmer or developer is coding something, so there can be some problems. So how we can fix those problems, how we can fix those bugs, right? And we will be talking about fundamental of discrete even simulations and NS2 simulations especially. So let's start. So in this part of the lecture, we will try to establish or try to justify why we need network simulation. So our motivations are, first of all, we will try to learn fundamentals of evaluating network performance via simulation, and then we because NS2 is a discrete event-based simulator, so we will try to discuss fundamentals of discrete event simulation, and then of course we will be talking about NS2 simulation. So first of all, why we need simulation. So there are a lot of different justifications we can give. For example, we want to design a system, irrespective that it's a network, maybe it's some system that involves some input, output, and maybe feedback. So we want to design a system. So there are certain parameters, boundary conditions, input, output, feedback. So you need resources in order to establish the system first, and then if you want to evaluate that system, so there are chances that you are not able to generate the worst input that you can provide and test by using your designed system, right? So this is one of the justification that we can. So the second reason is that if you want to change the design of the system, maybe very small change. So of course it's very difficult to change the design of the system. So maybe you have to modify certain elements, certain components, certain maybe infrastructure design, and then you will be able to apply that change. Maybe it's a small change, or maybe an average change, or maybe a major change. So you need to dismantle the system physically, and then you have to apply the change. So it's very difficult to do it again and again. So you want to change the system in order to test different, for example, configurations, maybe different feedback, and so forth. So it's very difficult to change the system. So when we talk about the analysis, evaluation of the system, right? So it's very difficult. It's very hard to do it practically, to do it real time. So what we normally do, we develop or design an environment, and we try to simulate that environment accordingly. For example, if we want to test a control system, or maybe we want to test a network, or maybe we want to test some other infrastructure, so we normally design and develop an environment that is not exactly the same, but it is close to the real one, right? So there is difference, of course. There should be difference, because real-time environment is always different. So, but at least we can analyze and we can evaluate very close to the real system. So these are some of the justifications, right? So here we have mentioned that if we have, this is the simulated environment, right? So here we have a computer program, and that computer program actually simulates deterministic rules governing behavior, and then we are observing. So of course a system, what we are doing when actually we are simulating a system, so we are observing the behavior of the system, and we are actually observing. And then this is the real one, right? So we have input, and system under study has deterministic rules governing its behavior, right? So then we have again boundary conditions over here, and here we have the program boundary. Okay, so why simulations, right? So here we have, so as mentioned, that real system, of course, not available. So if, for example, space, if I want to simulate a spacecraft, so it's not possible to establish, to go into this space, and then you establish a system there, and then you test it physically. So we use space simulations, then of course flight simulations. There are a lot of different softwares that actually provide flight simulations. Even the pilots are being trained by using those flight simulators. So what are the benefits? We can quickly evaluate design alternatives, for example, different system configurations, right? So here if we talk about the space simulation, so we can of course test different system configurations. Then we can evaluate complex functions, which maybe it's very difficult to design and develop and then implement and test. So by using a computer software, by using simulations, we can evaluate complex functions for which closed form formulas or numerical techniques are not available, right? And then of course here we have the precise definition is a flexible methodology we can use to analyze the behavior of a present system or proposed business activity, new product, manufacturing line, or plant expansion. So you have a plant and you want to expand it, right? So if we have a model of that plant before it was physically developed onto a system, onto a computer, so now in future, or now we want to extend it. So what we can do, we have the model, we can extend it on the computer, and we can simulate and see what are the possibilities, right? Okay, so by performing simulations and analyzing the results, so of course after simulation we will be getting some data, and we can evaluate that data, and in that case, in that scenario, we are actually analyzing, we have to analyze the results. So the advantage is we can gain an understanding of how a present system operates. So we know beforehand, before actually start developing the actual system, we know that how a system can operate and what would happen if we changed it, right? So you can also, because in simulation we have changes configuration, we have changes the connectivity, we have changed different scenarios, use cases, so we know the behavior of the system. So moreover, we can also test the worst conditions. So we can generate worst input for the system, and we can see the behavior of the system by using simulation. And here comes the advantage. We can estimate how a proposed new system would behave. But not always a simulation deals with uncertainty in the system itself, right? Okay, so we have different type of simulations. We can have discrete simulation and Monte Carlo simulation. So our tool which we are going to use, the NS2, that is a packet-based discrete simulation tool, because every the trigger of a packet, it's a discrete event, and it's a packet-based simulation tool, discrete tool, you can say. So when we talk about discrete event simulation, a discrete event simulation models the operation of a system as a discrete sequence of events in time. So if we talk about the NS2, so the arrival of a packet, the routing of a packet, reception of a packet, maybe the trigger of a packet, they all are discrete events, and they are recorded with reference to time. Each event occurs at a particular instant in time. For example, I'm interested in packet inter-arrival time, right? So if I'm interested in the delay jitter, so again I have to record the packet inter-arrival time, and then I will be calculating the jitter by using some formula, and marks a change of state in the system. Between consecutive events, so one packet arrives, then second packet arrives, so between consecutive events, if the arrival of a packet is an event, so no change in the system is assumed to occur, thus the simulation can directly jump in time from one event to the next, right? And then we have another simulation type, that is Monte Carlo method. It actually rely on random sampling of values for uncertain variables that are plugged into the simulation model and used to calculate outcomes of interest, right? So we have two different types of simulation, discrete and Monte Carlo. So here we have shown the advantages and disadvantages of the simulations. So here are the advantages. It's cheaper, so not all the time, so most of the time we should say. We can find bugs in the system, in the design in advance. Then we can use analytical and numerical techniques, and we can simulate system details at arbitrary level. And there are some drawbacks, of course. So there can be the use case or scenario where the simulation use case or simulation scenario does not reflect the actual system or real system in reality, right? So large scale systems, lot of resources to simulate, so we need intensive computational power in order to simulate large systems. So maybe slow if we don't have the computational power that is required in order to simulate the system, computationally expensive, and statistical uncertainty in results. So we can have statistical uncertainty. So this is the you can say footprint of the simulation. We can have numerical models, simulations, emulations, prototype, and operating system. This is the evaluation spectrum, or you can say evaluation footprint. So here we will be talking about programming a simulation, right? So time, so of course internal variable that keep track of the simulated time, system state variables that maintain simulation program, maintain the system simulation program defined state, system state, may track number of packets in a queue, and then current value of retransmission timer, and then events point in time when system changes state. Each event has associate event time, arrival of the packet to queue, departure from queue. Precisely at these points in time that simulation must take action. Then we have model for time between events, probabilistic, caused by external environment. So these are the key points, key elements when we have to take into account when we are programming a simulation. So here what we actually need in order to structure the simulation: maintains and updates list of future events, event list, well-defined set of events. So we should, because if we want to generate traffic, so there are certain you can say conditions that we have to define beforehand in order to program the simulation. For each event, simulated system action, updating of event list. Okay, so here we have the block diagram of simulator initialize event list, then get next nearest future event from the event list, and here is the timer, event timer. So here we are time stamping each event, and next after time stamping we will be processing the event, and again we can time stamp. So the difference when we stamp here and here, we can have the time stamp after the process, so we can calculate the service time in between. Change state, values, add, delete future events from event list, and then we have update statistics. So as I mentioned, so here we have the time, we have timestamp on the arrival of the event, and then after this process, after this service, we have another stamp over here. So we have actually updated the statistics and then done, and we can have a loop if we are not finished yet. Okay, so in the first part we try to establish that why we need simulation, and we try to relate some of the characteristics and the requirements to the underlying programming simulations. So now we will be talking about the simulation tool which we are going to use, that is NS2, Network Simulator 2. So first we will be talking about what is NS2, then how we can get NS2, how to use it, if you want to add your own stuff, then documentation and bug fixes. So actually it's a network simulator. 2 is the version. So because now we have also NS3, that is the version 3, but this is the most stable. We have a lot of different versions in 2. A package of tools, actually it's a bundle of tools that simulate the behavior of the network. When we talk about the network environment, network infrastructure, so 2 elements are very important regarding the network infrastructure. So one is the communication and the other one is the behavior. So communication involves routing, forwarding, switching, and so on and so forth, but the behavior is something else. So let me give you an example. So if we have a person that is standing at the entrance of an office, right? And he has assigned some duties to perform. So at the entrance of the office, his behavior is different. So when he is in the middle of the office and he has assigned some tasks, some duties, so his behavior should be different when he is in the middle of the office. So let me correlate this example to the routing. So we need a device that is called router in order to perform routing. So let's assume the person that was deployed within the middle of the office. So we have replaced that person with the router. So router, actually, if we talk about the two key characteristics, one is the behavior and one is the communication, right? So now the router within the core, within the middle of the office, he can perform two different duties or functionalities, its communication and its behavior. So you can see that the communication is very simple because it can perform routing, switching, and whatsoever is required, maybe forwarding, and so on and so forth. But the behavior has to be defined by configuring some of the policies and some of the rules, you can say, and we can update different files within the router. So the same behavior when that router is placed at the entrance of the office or at the edge of the office. So here behavior is different, and at the edge, at the entrance, behavior is different. But you can feel and you can realize that the communication at those two different points is the same. So maybe there is some minor difference or minor change, but it's almost the same. So here routing, switching, forwarding, and here again routing, switching, forwarding. So whenever, for example, a packet comes into the office, so it will be routing inside inbound traffic, and when a packet has to go out, so it will be forwarding the packet to the other. So, but the behavior is different. So because at the edge it has to block certain packets, maybe there are some attack, and within the office it has to behave differently depending upon the rules, policies that are implemented, right? So this is something we actually will be modeling and simulating by using the NS2 network simulation tool. So here you can see we have mentioned a tool that simulates behavior of the network. We can also simulate the communication because we can design a router that is routing by using our own protocol, right? So we can also create different network topologies. For example, star topology, mesh topology, bus topology. So we can design and create different topologies, and we can evaluate those different topologies according to our requirement. And then, of course, we will be actually logging events that are occurring during the simulation, and then after that we'll be analyzing those events in order to understand the behavior of the network. Okay, so here we have more details regarding NS2, stands for Network Simulator version 2, is a discrete event simulator for networking research development. So it works at the packet level. So here again the important point, because when we talk about end-to-end communication, so actually we are actually focusing on flow-based evaluation, simulation, or analysis. When we talk about maybe at the routing layer level or network layer level, so we'll be talking about the packets. So if we are at the application layer, maybe at the session layer, so we will be interested at the flow, because we can have maybe a voice communication by using different apps, maybe a video flow. So there are two different points over here. First one is the flow-based evaluation, flow-based simulation, and then the other one is the packet-based. So NS2 does not support flow-based simulation. It only supports packet-based simulation or packet-level simulation. So each trigger, each discrete event triggers a packet, maybe, or an event. So it provides substantial support to simulate bunch of protocols. So it supports a lot of different protocols. Even you can add your own protocol by using the core programming language, that is C++ and C. So we can it supports TCP, Transmission Control Protocol, UDP, FTP, HTTP, and DSR. So we can also have the provision of simulating wired and wireless network. Even if we have the heterogeneous network that includes wired and wireless network, so we can also simulate in that case, in that scenario. So actually the native platform for NS2 is Unix or Linux, but we can also use it by using Windows. So as in our previous lecture, we saw that we can use Cygwin in order to use the NS2 onto Windows platform. So it uses a scripting language. So actually there are different tools, there are different nodes, different devices, different maybe you can say protocols. So in order to bundle or glue all those different components, devices, we need a scripting language. So TCL is actually used to glue all those different components, nodes, and modules. Standard experiment environment in research community. So it's very popular in research community, used for network on chip simulation. So because in network on chip or micro level, so if I talk about macro, so it's the conventional network where we have routers, switches, bridges, and wires and cables, computers, and so on and so forth, maybe wireless devices. But when we talk about micro level, on the low level, on the chip level, so again nowadays people are using routers in order to route data, because there are certain applications where we need to use a lot of different processors, a lot of different memories, a lot of different ASICs. So actually there is the requirement that those different components, they should be placed in such a way that the transmission of data from one unit to another unit should be effective and efficient, should take less time, and should be power efficient. And there are a lot of different requirements. For example, we are actually interested to use one clock, that is for all the devices onto the onto a single board. So it is actually being used for network on chip simulations in order to design and develop routing strategies that are power efficient, in order to transmit data effectively and efficiently on such small distances, right? So and here there is again one main difference, that we have mentioned packet level. So in micro level, at micro level, we call packet a flit. So we will be using flit based event simulator, right? Simulator. So we actually can evaluate different parameters. Packet arrival, so here you can see flit arrival rate, latency, jitter evaluation, and topology. Because when we talk about the network chip, so there are a lot of different configurations of different devices, for example ASICs, ASIPs. So we can test different topologies, for example torus, butterfly, and mesh, and there are a lot of other topologies. So we can use NS2 in order to evaluate. So here is the environment for the NS2. So you can see we have event scheduler, right? So network components, those are actually designed in C++ or C, and here we TCL, CL, OTCL, and TCL 8.0. So what is the functionality, or what is why we are using bunch of languages? So objective and oriented support, OTCL, it's actually providing OTCL is actually providing object oriented support, and then we have TCL, CL. So you can see here we have the C++, and here we have OTCL, object oriented, right? So in order to link this C++, right, with this OTCL, so we are actually using TCL, CL, and here we need event scheduler, so that is residing here, and then of course data network components. We are actually have different network components that are developed in C++. So here is the implementation of NS2. So you can we have to generate or think about a simulation scenario. For example, we want to connect those nodes, and in between those nodes, of course, this is the channel, this is the link, and then in order to simulate, we need to write a TCL script. So here you can see this is the TCL script. So we need to glue different components by using TCL, and here is the core, that is the actual implementation. So it's a mobile node, it's this node, it can be a router, right? So this is the C++, so you can simulation scenario, then we have TCL script, and here is the core of the NS2. So why we are using different languages? So these are the major languages, main two languages, TCL, and that I have explained that in order to glue all those different components together, we are actually using TCL, and the core is actually written in C++. So detailed protocol simulations require system programming. So of course we need some system level programming language, right? So byte manipulation, packet processing, algorithm implementation. So we have to process packets. So then when we talk about bits and bytes, so we have to manipulate bits and bytes. So again, we need a system level language, and of course we need to implement different algorithms, and the speed, the real-time speed is very important. So turnaround time is slower. So simulation of slightly varying parameters. So if I want to change, for example, I have two nodes and I want to connect those two nodes, and in between I have a channel. That channel is actually having the bandwidth of 1 MB. So now I want to change the bandwidth. So if I don't have a TCL language that actually is providing or gluing those two different nodes or joining those two different nodes by using the channel, so I have to go back to C++, and then I have to write some code, and I will compile, and I will be launching the simulation again in order to change the channel bandwidth. So what we normally do, we use TCL in order to configure certain parameters. So varying parameters or configurations. Scenarios, so as mentioned, we can have a lot of different simulation scenarios. For example, I am interested to evaluate this configuration by using different bandwidth, by using different delay, right? And if we have more than one if we have a certain topology where we have a lot of different nodes, so I want to test different topologies. So we can have a lot of different scenarios, right? So TCL provide us facility in order to quickly design and develop those different scenarios. So iteration time is again important. So we can have other simulation tools, for example OpNet. So it's a commercial tool, and again we can use it on Windows and Unix, and we also have the graphical interface, and you can drag and drop different nodes, different components, and then connect them. But this is not free, you have to pay. And then there is some tool that is actually designed for wireless environment, wireless networks, Lomosim, and it provides certain features, scalable to support thousands of nodes using layered approach, and it's again open source, but for universities only, for educational users only. And then we have some other tools, and you can explore them by yourself. So now we are actually starting that what is NS2. So here we have the basic architecture. So you can see we have TCL simulation script and simulation objects. Those are designed in C++, right? And this is the TCL-CL simulation objects, right? And here we have the trace file, and trace file can be used by NAM, network animator, and we can also use this trace file in order to plot the graph. So here we have different directories, right? And the hierarchy of NS2, you can say NAM, NS2, TCL-CL, OTCL, TK box, TCL box. And in TCL we have examples. We can also test in order to validate our NS2 tool, and here we have the library. So here we have the image graphically showing that how NS2 works. So you can see we have a scenario, topology, and traffic conditions, and that is actually developed by using TCL, right? So this is some file.tcl, and then those that TCL file is actually calling different functions, maybe different classes from this core, right? And then actually it's glued, it's binding all those different functions, classes, and different objects all together, and then actually is simulating the actual scenario and the topology. And after the simulation we can have the ASCII trace file, that is .tr, and that tr file can be used in order to plot the graph by using xgraph, or we can have another we can use another tool, that is NAM, network animator, and here we have the .nam file, and after having this file we can play this file by using the network animator. So how to get it? So it's very simple. So you just have to download from this site, and you can compile it locally if you are using Linux. So there are if you are using Ubuntu, so you can download and even install by using its software center. If you are using an older version of Ubuntu, so you can use Synaptic. So on the other side, if you are using Windows, so we have already shown that how you can install it. You can use actually Cygwin. So moreover, there are other repositories that also are providing NS2, but this is the official and main repository where you can get NS2, right? So first of all, so how we actually are going to generate a simulation scenario. So first of all, we will be thinking about the topology, so how the components and different cables, they are interconnected. Then we will be, after generating the topology, putting the tools, connecting them, and then we will be deciding about the protocol, the bandwidth between different links, delay, and the packet size, and so on and so forth. So, and then after that we will be getting traces, right? And then finally we will be using the NAM, or maybe plotting the X graph. Load output files in TCL script. To run, we need to put ns. This is the name of the file, .tcl. It initiates C++ classes based on the TCL script. So it is actually, the TCL script is calling different classes, functions, objects in the background form of trace files. So here we have a simple example. So here we have created a very simple topology. So this is node N1, this is node N2. So they are connected together by using this link. You can say this is the channel. So the bandwidth of this channel, this link, is 1 megabit per second, and it is providing a latency of 10 millisecond. So here is the code. Create a new simulator object. So of course we are using TCL set ns new simulator name trace file. So if we are interested in playing, then we have to create name file in F, open out.nam w, name trace all nf, right? So define a finish. So we have to finish here and then close the trace file. So of course after opening the file we have to formally close the trace file, and then finally we will be executing the name file, exec nam out.nam, and this is the, after the initiating the NAM player, we will be exiting. So topology, 2 nodes, set N0, this is node 0, NS node, N1, this is node 1, NS node, and then we are creating the link. So we can define simplex, duplex links. So this is a duplex link, so we can have both way communication between the nodes. So duplex link, and the links is actually established between node N0 and N1. This is the bandwidth, this is the latency, and this is the traffic type, drop tail. So again here we have more than 2 nodes, N1, N2, N3, N4, N5, and N6. So you can see this is node N1, and the arrows are indicating duplex link, right? So both way communication, 5 MB megabit per second. This is the bandwidth of this link between N1 and N3, and this is the latency, right? And then we have N3, N4, but here something is different as opposed to N1 and N3. So between N3 and N4 you can see the arrow is only one directional, so it means we can have only simplex one-way communication, right? Okay, and if we look at N4 and N6, so again here two-way communication, 300 kilobit per second, and we are having more delay over here, 100 millisecond, right? And set properties like queue length. So here I have mentioned, so drop tail, that is the queue type. So that was not traffic type, queue type, right? So queue length, location, and protocols. We are interested in routing algorithms, so we have to, whenever we are defining a node, So we have to set all these properties. Queue, length, what is the length of the queue, location, then protocol we are going to use, routing algorithms. So whenever you are declaring a link, so set type of the link, simplex, duplex. So we can also generate or create wireless link and satellite link. So of course bandwidth, set the bandwidth, and latency. So all is done using TCL. So here we have we actually are adding traffic. So node N1, N2 bandwidth, this is the latency. So here you can see this is the agent UDP mentioning the protocol. You can see protocol, or you can say protocol agent, and then we have CBR, constant bitrate. So that is the source, traffic source, and this is the link. Packet size 500 bytes and rate 800 kbps, kilobits per second. Constant bitrate traffic. So if we put all together, right, so here you can see a UDP agent and attach it to the node 0. So set UDP 0, new agent UDP. So we have attached this to some node, and traffic source, and attach it to UDP 0. So we have here the protocol. So of course we are using protocol in order to transmit certain bits and bytes. So we are using a traffic source, that is CBR, constant bitrate. New application traffic, CBR, right? So then we have to mention the packet size. So this is the packet size, and set the inter-arrival rate, so packet inter-arrival rate, and again we have to attach this source, right? So you can see here they are attached together, traffic type and this null agent, that is so that is the source, and here we are defining sync, right? Create a null agent, traffic sync, and attach it to the node N1, null 0. So now we are attaching this sync and source. So connect the traffic source to the sync. So here you can see we are connecting traffic source to the sync, and this is the scheduling, right? Start CBR 0 start, and this is the scheduling, right? So you can see time 0 point, we have started here, then we are stopping here, and this here we are finishing after 5 seconds, right? And then of course after writing this code we have to run the simulation. So now we will go for another scenario, and this scenario is taken from NS2 by examples, right? So you can see we have the scenario, we have 1, 2, 3, 4 nodes, and we have interconnection of these nodes. So you can see N0 is connected with N2, and the bandwidth is 2 megabit per second, and latency is 10 millisecond. If we talk about N1 and N2, then you can see the channel is 2 megabit per second, and again delay is 10 millisecond. So here bandwidth is N2 and N3. For N2 and N3, bandwidth is 1.7 megabit per second, and the delay is 20 millisecond, and this is sync, and this here we have null, right? And you can see here we have the protocol and the application, right? So protocol and the application traffic. So FTP traffic, CBR traffic, right? So this is the sync. So all the traffic has to sync here, right? FTP and CBR in red. Okay. So here we have the code, right? NS new simulator. We have to create a new simulator object. So now we are defining different colors for different applications, for different data. So color 1 blue, color 2 red, right? So here we are actually opening the nam trace file, nf nam file, open out.nam. This is for writing, and nam trace all, right? So finish procedure. So this is the finish procedure. Proc finish. This is the finish procedure for this, right? So for nodes, right? So you can see N0, NS node, N1, N2, and N3. Now we will be creating them, right? So duplex link between N0 and N2. So you can see N0 and N2. This is the bandwidth, this is the delay, and this is the queue type, drop tail, right? NS duplex links between a link between N1 and N2, N1 and N2, bandwidth, delay, and this is the queue type. N2 to N3, 1.7 megabit, 20 millisecond delay, drop tail. Queue size, right? So this is queue type, and here we have to mention the queue size. Queue limit, N2 to N3, N2 to N3, that is 10. So we can queue 10 packets. Position for NAM, duplex link up, N0, N2, orient, right, down. So here we are mentioning actually the position of different nodes for NAM. Duplex link up N1, N2, N1, N2, orient right up. Duplex link N3, orient right. So here we will be monitoring the queue for link N2 and N3. Okay, so here you can see we are actually attaching the application agent, new agent TCP, class 2 agent and not TCP, and again we have to define, this is the source and this is the sink, and set up this is the application, right? FTP over TCP connection, new application FTP, attach agent TCP. So this is application. If I have mentioned FTP as a traffic type, so that was wrong. So FTP is an application actually. And here we are setting up the UDP, right? So here TCP agent, we are using TCP agent between attaching TCP agent at N0, and here we are attaching UDP agent at N1, right? And so this is the source and this is the sink, right? And here we are setting up the traffic type CBR, right? Packet size, so when we are establishing the traffic type, so we have to establish the packet size and then packet rate, right? Schedule events for CBR and FTP, right? So start, and this is FTP start, CBR start, FTP start, and FTP stop, and CBR stop. So you can see that we have started the traffic type first, then the FTP, that is an application type, second, and then stopping the FTP first, and then CBR lastly, right? And then detach TCP and sync agents, right? So here we will be detaching them and call, here we have to call the finish procedure as usual, and here we are actually printing CBR packet size and interval, right? So of course we need to run the simulation. So after having running the simulation, what we can do, right? So we actually are interested in the evaluation of the behavior of the network. That is because I've mentioned the communication almost remains the same, routing, switching, forwarding, but we are actually interested in the behavior in a certain scenario. For example, in a certain topology, by using certain applications, by using certain queue length, or maybe using a certain size of the packet. So we want to observe the behavior, right? So okay, so here you can see we have now different metrics, right? So this is the time. So we can also take the example of packet inter-arrival time, right? Or maybe the packet service time. So we have stamped the packet first as it arrives at a particular node, and when it left the node, then we can again timestamp and we can calculate the different, and this can be the service time at that particular node. And then you can see here we have IPs, so we can have source IP, destination IP, and so on and so forth. So actually we can collect different parameters or extract different parameters. For example, packet service time, packet inter-arrival, delay, jitter, and we can evaluate and plot them according to our requirement in order to observe the behavior of the network for a particular scenario. So here we will be talking about the visualization tool, that is network animator, NAM. It plays events, or you can say, because the events are already recorded, so you can say replay events from a NAM trace file. NAM trace file can be huge, right? So of course we are recording the events, so there are a lot of packets that are flowing here and there, so we have to record a lot of different data. When simulation time is long, our events happen intensively, right? So this is the command you have to run, nam-a, and this is the name of the trace file. Okay, so this is the graphical view of this visualization tool. So you can see we have nodes over here, and you can see that the colors, they are flowing, so they are actually showing packets flowing. So here is the X graph. We can also plot, use the data in order to plot different graphs, right? So how to add your own stuff when we are interested to add our own protocol, and you want to add a specific node, or maybe you want to design a router that is routing by using, that is performing the routing functionality on the basis of your own algorithm. So you can do that within NS2. So first of all, you need to create the class, right? So of course, after creating the class, you should be able, or you need to create the OTCL linkage, because we have shown in slides previously that there is a linkage between C++ and the OTCL, right? Okay, TCL. So you can find the tutorial over here if you want to add your own protocol in NS2, right? And then of course, as it is an open source, the documentation is not user friendly, so but there are a lot of different resources where you can find different tutorials, different examples, and you can even straight away download the file and run by using the NS2, and you can understand how it is working. So information about OTCL interpreter, C++, class hierarchy, parameters for various protocols. So this is very good resource for regarding the documentation. Okay, and then we have a lot of different tutorials. NS2 tutorial by Mark. Then it includes examples, lot of examples, right? So here we have another documentation, NS2 for beginners. It is again by Mark. Okay, and then this is the, because you need to understand TCL, so here is the link for TCL tutorial, and then of course bug fixings. So of course it involves scripting language, or if you want to add your own stuff, so it involves core programming. So there can be certain bugs, right? So first there are a lot of different mailing lists, so you can use those mailing lists if you come across certain errors. And there are chances the problem you are facing, the same problem is faced by other people, right? So the response, the mailing list people that are active on the mailing list, they respond quickly. So you can also use built-in examples, right? So there are a lot of different examples, as I mentioned, NS2 examples by Mark. Right? So there are certain steps when things go wrong, so you can follow those different steps in order to find what's going wrong. So first of all, you should look at your code. So maybe you are not using the proper format, or maybe some errors, so maybe you have not attached some application, so you have joined the nodes, but you have not properly mentioned the requirements, or you have not mentioned the parameters that are required to connect these two nodes by using some channel, right? So you should look at your code. So here some of these steps are maybe questions you can ask yourself. Expected behavior of the network, right? So first of all, you should verify that all the nodes, they are connected properly, right? So and then you should record the data properly. You should have the log, right? So logging trace information at a right level. I change it to narrow down on the problem. Has anyone else out there had the same problem? So of course you can use mailing list. So maybe somebody else is having the same problem. So if you spend 2 hours or maybe 4 hours to solve this problem, so maybe he and she can answer in minutes, and you are able to solve this problem. Similar in examples that I can look at, right? So code really do what the protocol says, right? Okay, so that's all for today's lecture. So today we have talked about NS2, that is an network simulator, and we have talked that what is NS2. Then after that we discussed where you are able to find it and how to use NS2, because that is very important. And we have also gone through some scenarios, some use cases where you can understand that how you can generate a scenario in order to simulate your own network, your own use case. And then if you are interested to add your own stuff, for example, you want to add your own protocol, you want to add a new node, you want to add a new router or maybe something else, so you can use you can add this stuff in NS2. So of course, as this is a tool that is used for network simulation, so you need documentation, you need tutorials. So despite the fact that it is an open source tool, so conventionally and normally the documentation for open source tools, they are not user friendly, but for me, for NS2, you can find maybe not very user friendly, but you can say good documentation in order to grab the tool. So we can you can have different tutorials, different tools, and you can go through and you can grab the tool. Then of course, when we talk about generating the simulation scenario, adding your own stuff in this tool, or maybe creating some topology, so or adding your own protocol, so you need to write some code, right? So for example, TCL code, or maybe you are adding in the core, so you'll be writing C++ code. So there are chances that you will be facing some bugs. So there are some methods you can use. You can use mailing lists, you can look at your code, or you first there are certain steps you can follow in order to trace the bug. So we talked about the bug fixing. So this was about the second part. So in the first part we try to justify that why we need to simulate, right, and what are the advantages and what are the disadvantages of the underlying simulation. And then we talked about different types of simulation, and those are discrete and Monte Carlo. And NS2, the tool which actually we are studying, is a discrete event based tool. So that's all for today's lecture. मेरी तरफ से अल्लाह हाफ़िज़, अस्सलाम वालेकुम.